A neural network is a popular and adaptive machine learning algorithm that was inspired by the structure of the human brain. A neuron has many inputs and a single or multiple outputs. When constructing a neural network, we first have to build the structure. A neural network is made up of neurons or nodes that process data and produce an output, represented as a circle. The number of nodes in a neural network is preset by the user. The usual structure of a neural network is as the following: an input layer, a hidden layer or hidden layers, followed by an output layer. To explain the maths behind a neural network, we look at the simplest form of a neural network with simply n inputs and a single output. This is known as a perceptron. So step 1, we build the structure of our neural network. For step 2, we set our weights and our biases. For each connection between our input layer and hidden layer, or output layer in this case, there exists a weight W1 to Wn. This is used to transform each of our input features x1 to xn. The weights are initially randomly set, but then are optimized later. We also have the option of adding a bias term, represented as b, which enables us to add more variance to the model if we wish. Step 3, we process the input data. We take our set of inputs x1 to xn and we combine it with our weights and our bias. And we do this by taking the dot product of our inputs x and our weights w and adding the bias term b. And we label the name of this output as z. So z equals x.w plus b, which equals x1 w1 plus x2 w2 plus ... all the way to xn wn plus our bias term b. We can then apply an activation function to this output z, which essentially will convert this value into a probability between 0 and 1. This is commonly used in classification tasks. This is done by applying the following function. So 1 over 1 plus e to the power of minus c. And the output of this is stored under the label name y hat. Remember, for the first stage, we just randomly set our weights w1 to wn and our bias b. So the output of this y hat will just be a random probability between 0 and 1. But we want the neural network to detect patterns and trends so that it can use these trends to form predictions or to unveil certain relationships within the data. So we now need to go ahead and update our weights and biases, which we can control so that our output is not as random. For that, we need to look at a loss function. So here we're selecting the mean squared error as our loss function. This gives us the average distance our predicted values are away from our actual values squared. So n here is represented as our number of instances, yi our actual output value, which we store in our training data, y hat I, which is our predicted output value, which we demonstrated how to produce previously. So next we want to optimize our weights and our bias. We do this via gradient descent, which we explained in episode 4.2. For gradient descent, we need to figure out the partial derivatives of our cost function with respect to what we want to optimize. So in this case, it's our weights and our bias terms. To calculate the partial derivative of our cost function with respect to our weights wi, we utilize the chain rule. And I won't go into too much detail in the maths for this episode, but we require 3 elements which we multiply together. We also calculate the partial derivative of our cost function with respect to our bias term b. Now that we have the partial derivatives with respect to our weights and bias, we can apply the gradient descent algorithm, which we covered in episode 4.2, to optimize our parameters. We update the values of our weights w and our bias term b according to the following equations. We introduce the hyperparameter alpha, which determines how we approach our optimal values. This often ranges between 0.001 and 0.1. Now, the process of going forward through our network to produce an output, which is initially random, is what is known as forward propagation. And the process of going backwards and updating our weights and our bias so that we reduce our cost function is what is known as back propagation. So we go through forward propagation and back propagation, and we repeat this cycle until we converge. That is, there is not much change to our model's performance, or we reach a user set number of iterations. So here we gave a worked example of a very simple neural network with no hidden layer. Often neural networks have hidden layers that enable an additional set of weights to be applied to the output of the previous layer, adding more complexity to the model. However, enables a model to handle more complex data. Thank you guys very much for watching, and I hope you learned something new.